We're continuing on here, chapter 10 still with energy. And obviously, last time we talked about kind of an important sort of representation of energy, and that is what is referred to as delta H, which is the change in enthalpy. And the change in enthalpy is really used, as we talked about, to sort of represent, for example, in a chemical reaction, what is sort of happening? Is it sort of going to release overall some energy? Will it need to sort of absorb some energy? And remember that one of the ways that we calculate delta H and energy, since it is a state function, is that we basically take the delta H of our products and we minus it from the delta H of our reactants. Once again, here, the way we find our delta H values of our products and our reactants is they are usually in a table. And we look up those values and basically take all the energy of our products from those tables minus all the energy from the reactants. Remember as well that as we talked about and as we did in some of those, if there are coefficients in those balanced equation, we do have to multiply the values we find in that table by those coefficients when we do that. Really, the reason why we're doing that is, as we talked about, in a chemical reaction, we have our reactants going to our products, and a state function is basically the difference between your final state, which is really your products, and your initial state, which is really your reactant. So that's why in a lot of these sort of calculations we talked about, we do kind of take those kind of products minus the reactants, give us that difference in kind of final state minus initial state. Remember that as a reaction takes place, really the only thing that's happening is bonds are being made and bonds are being broken. And we can look at an energy diagram where on the y is energy and the reaction is sort of progressing. And we could actually look at where our energy of our reactants are to our products. And there is this hill of energy that the reactants has to climb as they're starting to break those bonds and starting to make new bonds. And that is what is known as the activation energy. And that is sometimes abbreviated E of A. And that's really the minimum amount of energy that's required for a reaction to take place. It's really the energy barrier there is between the reactants to the products to make products. Thank you. Now, when we get to the very top of this hill, even though it's caved in on my drawing, that is what is known as the transition state. And at the transition state, you usually have sort of a complex, which is a sort of high energy intermediate where you have bonds that have been sort of partially broken from the reactants and these kind of new bonds being made on the product side. So you got these partially made bonds, partially broken bonds, and it's really the highest point of energy in a reaction, and that usually makes it quite unstable, that activated complex up there at the top, and it usually will come down to our products. This is a exothermic diagram because if we take the difference between the energy of our reactants and the energy of our products, that is the delta H of the reaction. And again, as we talked about, if we take the delta H here in this particular example, our products, which are lower in energy, will be a smaller number than our reactants, which is a higher energy number. So a small number minus a larger number will yield us a negative value for delta H, and again, that is exothermic. Opposite is true. If you had an endothermic diagram, it would look very similar, except that the reactants actually will be lower in energy than your products. And once again, here, that would be your activation energy. And in this case, our products are actually higher in energy, so we're going to have a larger number minus a smaller number, and that usually will give you a positive value, and that means that it is endothermic. So delta H is really important in the sense that if you are given the delta H value for a reaction, or even if you're able to calculate it yourself, it will pretty much just really by the sign, the number's not all that too much important, but just by the sign, whether it is positive or negative, you will know whether or not the reaction is exothermic or endothermic. And as we also talked about, really important to make sure you don't ignore the sign, especially when you're calculating energy. So again, if you get a negative number, it is sort of important. Obviously, the activation energy hill there is the energy barrier to get to the other side. It also kind of determines the rate of a reaction. One way that you, for example, can speed up a reaction is by adding what's known as a catalyst. And when you add a catalyst, you can speed up a reaction. It typically will speed up a chemical reaction. A catalyst is not a reactant. It is not a product in the reaction, and it does not get used up actually. Really, a catalyst's sole function is to find a more efficient way for that reaction to take place. And by doing so, it allows reaction, usually in most cases, to occur faster. Ultimately, if you go back to sort of our energy diagram, if you have sort of this reaction here, reactants to products, in a uncatalyzed reaction, the reactants has to climb all the way up here to get to the other side. By finding this more efficient pathway for a reaction to take place, a catalyst will actually typically lower the activation energy. And by doing so, what that's going to allow is more reactions to get to the other side quicker. They're going to have enough energy to kind of get up and over, and you're going to see probably an increase in the rate of reaction. So by finding that alternative pathway, like I said, it can really speed up a chemical reaction. So, for example, if you did ammonia, the formation of ammonia, it's a really slow reaction, but if you use a catalyst, it will go really quick. And sometimes catalysts are just metals. They can also be acids or bases used as a catalyst. If you look at a chemical equation, a lot of times on the arrow, you'll see something maybe like platinum written, maybe an H plus or things like that. These are typically where you see the catalyst listed in a chemical reaction. It's kind of listed there on the arrow. And what it's able to do is, again, for example, if you had gas molecules just flying around, in order for that reaction to take place, they would have to find each other and come in contact with each other and just kind of hope they kind of come across each other. What something like a catalyst can do is, for example, instead of those gas molecules just flying around, if it's like a piece of metal, maybe those gas molecules are attracted to that piece of metal. And what that does is kind of put them closer to each other in a more efficient pathway. And they're most likely going to start kind of colliding with each other a lot quicker than they would if they were just kind of flying around by themselves, trying to come in contact with one another. We finished up talking about specific heat and specific heat capacity. And there's a formula which is Q is equal to ms delta T. Q is heat, or energy, and that usually has units of joules or calories. M is mass, which typically has units of grams. S is the specific heat capacity. And that has units of joules per gram per degree Celsius or calories per gram per degree Celsius. And lastly, here's the change in temperature, which we always want to go final temperature minus initial temperature. This is actually in degrees Celsius, which is, again, one of the few sort of things that stay in degrees Celsius when we use temperature. The specific heat capacity of liquid water is a number that you're responsible to know. That's a 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. So we could use this value here, Q, to figure out how much heat or energy is being released. And Q, much like H, kind of works the same way. If you have a Q that is negative, that's usually an exothermic process. And if you have a Q that is positive, it's an endothermic process. Pretty much all energy kind of rolls that way. If you end up with a negative number, any type of heat or energy that you're calculating is going to be an exothermic situation, and any positive number going to be endothermic. As we also talked about, probably the most important part of this calculation in terms of helping you correctly determine exothermic or endothermic is the change in temperature. As the mass value, there will always be a positive number. The specific heat capacity will also always be a positive number. So really the only way you could kind of turn Q into a negative number is that change in temperature. And again, that's why you want to do the final minus initial, so that if you do end up with a negative change in temperature, that's going to give you the proper negative value for Q and tell you it's exothermic, which is what we would expect. Again, the final temperature in an exothermic process for somebody should be less than where it started with, right? Because it's releasing all that energy, its temperature should go down, as opposed to an endothermic process where it's gaining all that energy, its final temperature should go up. Any questions on any of that there? All right. So we're just talking about our specific heat, which is kind of where we laid up. Once again, here's some specific heat of some other substances. You again do need to know this number, and also its sort of calorie equivalent. Not joules, calories per gram per degree Celsius. Remember as well, that is the conversion between calories and joules. 1 calorie is 4.184 joules. So as we talked about towards the end last time, if you have a high specific heat capacity, it's going to take a lot more energy to see a big temperature change, right? Depending on the mass that you got going on there, and as opposed to something with smaller. Also, you want to make sure that you do find it in the correct sort of phase. As you can see, liquid water is 4.184, but ice and steam are actually closer to 2. So it does make a difference if you're not in, for example, if you're dealing with water, if you happen not to be in the liquid stage, you do have to use a different number for specific heat capacity of water. I would say probably 9 times out of 10 is going to be probably in the liquid state in most cases. And that 4.184 number is going to be what you're going to use, but sometimes it may not be. And obviously other substances there have obviously here different specific heat capacities. All right, so why don't we try a calculation here. We want to determine the amount of energy or heat that's required to raise the temperature of 10 grams of aluminum. Has a specific heat capacity of 0.89 joules per gram per degree Celsius as it goes from 25 to 58 degrees Celsius. Give your answer both in joules and calories. So why don't you take a few moments there and see what you come up with. Look, so we are looking at some specific heat. So we want to use our equation. Q is equal to ms delta T. Let's pull out some information here, which is usually a pretty good idea to do. So we're looking to determine the amount of heat as energy as heat there. So we are looking for Q. Obviously, 10 grams is a mass. We have the specific heat capacity given to us here, 0.89 joules per gram per degree Celsius. We have our initial temperature of 25 degrees Celsius and our final temperature of 58 degrees Celsius. And that means we pretty much got everything on this side, so we'll just pop it in there. So Q is equal to 10 grams times our 0.89 joules per gram per degree Celsius. Once again, we do want to take final temperature here, which is 58, minus our initial temperature, which is 25 in this particular case. That's going to get us here. That's going to give us on the calculator about 293.7. In terms of units, the Celsius cancel, the grams cancel, does leave us with joules as our unit. We also need to kind of look at maybe some sig figs here. So we're multiplying. That is 3 sig figs. That is 2 sig figs. And when we do the difference here, we get something like 33, and that's going to be 2 sig figs as well, which means technically we probably should end up there. That's going to take us to 290 joules in this case. Any questions on that calculation? Yeah. For which one? Specific heat capacity has two sets of units. It's either joules over grams degree Celsius, or it is calories over grams degree Celsius. It's either one of those. They're not the same because the difference, as we need to do here on this question, is convert it from calories to joules or joules to calories, and it's 4.184 is the relationship between those two. You would use the one. Um, Really, probably it'd be based on your specific heat capacity that you look up. And I would say in this book and probably in this class, most of the time it's going to probably be joules over grams per degree Celsius, but it can be calories. But so it would be based really on that specific heat capacity. Or if you were solving for the specific heat capacity, it would be based on the unit of energy or heat there for Q, whether it's joules or calories. And that's why joules or calories can be for Q as well. There's no joules or calories. Either joules on top or calories on top. They're not together ever. Yeah. And that's really the definition. Why it has three units is that's the definition of specific heat capacity. Definition of specific heat capacity is the amount of energy, which is either a joule or a calorie, to raise 1 gram of a substance by 1 degree Celsius. So that's what basically the definition is, and that's why it has all three of those units. We will convert this into calories, which is the other part of the question it asked for. And in this case, 1 calorie is 4.184 joules. The joules will cancel. We'll use the rounded number here, 4.184. Be about also 69 calories in this particular case. Any questions on up there? Yeah. You can, and probably most of the time I probably would use that. The only reason I used a round number here is it did want the answer in joules, so we want to kind of clean it up, but it would have been okay as long as you rounded it off to two sig figs, like 70-ish maybe, or 71 or something like that. You would think you maybe switch it up with. Other questions? Yeah, that's what the question asked, right? It asked for both. There you go. Yep. Other questions? So usually, obviously, if it doesn't ask, then you would probably end up in a question like that and just joules and give it as that answer. All right, why don't you give this one a go? 294 joules of heat is transferred to 10 grams of silver at 25 degrees Celsius. What will be the final temperature of the silver? And the specific heat capacity of silver there is 0.24 joules per gram per degree Celsius. Okay, so let's take a look. So once again, obviously, we're using our specific heat equation. Q is equal to ms delta T. We'll pull out some information. So 294 joules is heat or Q. And remember, again, the good way to remember it is Q should only have one unit, either joules or calories. Again, the specific heat capacity has those three units associated with it. Sometimes people really confuse those two as to where to put them. Bless you. 10 grams is a mass. We have obviously here our initial temperature of 25 degrees Celsius. We're looking for our final temperature. And we have our specific heat capacity as 0.24 joules per gram per degree Celsius. So putting it in here, we are going to actually solve for the change in temperature, since we're looking for a final temperature. That means that these two guys here need to be divided to the other side, and that will give us the change in temperature is Q divided by ms. Putting in our units here, our numbers, we will end up with 294 joules divided by our mass here, which is 10 grams, and divided by our specific heat capacity, 0.24 joules per gram per degree Celsius. Joules will cancel, grams will cancel. That will leave us degrees Celsius, which is good since we're looking for a temperature. and it will flip to the top once we divide. And we'll go at 294 divided by 10, hit equals, divided by 0.24, hit equals. This is going to give us 122.5 degrees Celsius. A reminder of a couple of things at this point. This is not our answer. This is only the change in temperature. This is not the final temperature. The change in temperature, as we know, is the final temperature minus the initial temperature. So here we would be looking for our final temperature will be the change in temperature plus the initial temperature. And in this particular case, I am actually not going to do rounding here, since this is not going to be our final answer here. And obviously, we'll be a couple degrees off if you kind of round it at this point. So I'm just going to keep the whole number and kind of keep track of where I should end up at the very end here. So this is going to be 122.5 plus, again, our initial, which was 25. And that's going to give us here 147.5 degrees Celsius as our final temperature. Now, in this particular case, I do need to kind of keep track and sort of figure out where I should round at this point. So we do want to kind of go back to our first calculation here, which was basically this multiplying and dividing. And that means that we should be looking at significant figures. So our top number there had 3 sig figs. This guy has 3 sig figs. This guy has 2 sig figs, which means technically if we did round and we were going to stop right here at the change in temperature, this technically should have been 120 degrees Celsius, right? Rounded to 2 significant figures in this case, which is actually a whole number. And that's important because technically speaking here, this is a whole number. And this is actually a whole number. And we're looking at decimal places here. That means that we should take our final answer to a whole number as well, which means we would round to here, and we would have to go up, so about 148 degrees Celsius. So once again here, if you kind of used a rounded number, you're now at 145 degrees Celsius, and that's a good little difference there in temperature. So in this case, because it's not our final answer, that change in temperature, I would not round in this situation till the end. Yeah. Any questions on that there? By the way, the temperature here, our final temperature makes sense based on what we're seeing. It has transferred, this silver picked up 294 joules of energy. That means it's endothermic for our silver, and we would expect obviously its final temperature to be higher than it started at, right? So obviously if it went down, that's not what's happening here, because it's actually absorbing that amount of energy. Any questions on that? Now, the next thing we're going to talk about is if we have a transfer of heat or energy from one spot to the next. So as we talked about last time as well, heat does transfer from hot to cold. So for example, what happens if we have a lovely beaker of water here, and let's just say the water's at 25 degrees Celsius, and let's just say we have, I don't know, 115 grams of it. And obviously here we know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. Let's say, though, that we took a piece of metal, like you'll do next week. Take a piece of metal. And let's say we heated this piece of metal up to an initial temperature of like, and we'll go with 99.0 degrees Celsius. Let's just say it had a mass of, we'll do 52 grams. And we want to know what is the specific heat capacity for the metal. So we're trying to figure out what is the specific heat capacity for this metal. So what we want to do is we're going to take this metal, and if I throw the metal into this water, and it goes in, what should happen in terms of energy? Should the water gain or lose energy? Should gain energy, right? And the metal should lose energy. in heat because it is hotter, obviously, than the temperature of the water. So our transfer of energy in this case is going to go from the metal basically out to the water, right? And that means for the metal, it's an exothermic process, right? And for the water, it's an endothermic process. It's going to actually absorb that energy. Now, if you put that piece of metal into that water, it will eventually rest at a final temperature that is actually the same temperature as the water. So let's just say the water's temperature after you put the metal in went to 27.5 degrees Celsius. Once that metal is in there, like I said, it will eventually equilibrate to that final temperature of the water. And one of the nice things about that is by just really following the temperature change of the water, we will also know the final temperature of the metal in this made up example will be 27.5. It will be the same for both the metal and the water. And this is really good because if we think about our specific heat sort of equation and we do it for the water, we have all the information we need for water to basically calculate how much energy is going to be absorbed by the water. We have the mass of the water, which I went with 115 grams. We have the specific heat capacity of liquid water. And we have our final temperature, which is 27.5, minus our initial temperature, which is 25.0. And for the water, we could actually just figure out how much energy was gained in this case. So if I do that there, 27.5, 25 times 4.184 times 115. That's going to give me here 1202.9. Once again, here grams are going to cancel, Celsius is going to cancel, joules. And this right here is a positive number, which means it's endothermic. And this is the amount of energy, obviously I didn't round anything yet, but this is the amount of energy that was absorbed by the water when you put that hot piece of metal into it. First off, any questions on that? So why is that helpful? So we talked about sort of transferring energy as being sort of like a nice perfect transfer of energy, which means if somebody loses a certain amount of energy, somebody else will gain the exact same amount of energy. In this particular example, the only thing that's going to provide energy to our water is the piece of metal we threw in there, right? Which means if I know how much energy was gained by the water when the metal went for a swim, I will also know how much energy was lost by the metal, right? Because all of it had to come from the metal into the water to basically raise its temperature. So there is a relationship in a situation like this where Q of the metal is equal to negative Q of the water. So when we talk about Q of the metal, we now know that Q of the metal is this exact number that the water gained. The only difference for the metal is it's an exothermic process, which means it's actually the negative version of it, 1202.9 joules. Once again here, I'm not going to round because I'm going to kind of use this number in another calculation, but I do want to kind of keep track of things, and we'll go back and kind of figure that out in just a second. First off, any questions on that there? It's negative because the metal is losing energy, which means in terms of the metal, it is exothermic, and a negative value of Q is an exothermic process. Just like over here, this is a positive number, and that is an endothermic process, and that's what's happening for the water. It's gaining the energy, endothermic, positive value. All that energy had to come from the metal, which is an exothermic process, releasing the energy, and it's going to be a negative value. The amount of energy is the same, conservation of energy, right? We don't lose it anywhere, right? It's all conserved. So the number is exactly the same, and the only difference between those two values is the sign. So that's why we were talking about earlier. It's really, really important not to ignore the sign, right? When you're doing energy, because it kind of tells you things. Other question? That's also very helpful because now if we think about the metal, which is ultimately what we're trying to figure out, the specific heat capacity, if I go to the metal now and I do Q of the metal with the exact same formula, ms delta T, I could actually solve for S by dividing those two guys to the other side. And that will give me, that's the specific heat capacity is equal to Q of the metal divided by the mass of the metal and the change in temperature of the metal. And by using the water as a way of figuring out how much energy was lost by the metal, it allows us really to complete this calculation here. So if we do that, we're going to go with the negative 1202.9 joules divided by our mass of our metal, which is 52 grams. Also really important here for the metal, the final temperature is 27.5. The initial temperature is 99. So we do want to take 27.5 minus 99 degrees Celsius. That's important because when I do that, what type of number do I get? Positive or negative? I will get a negative number here. And that's really good because this is also a negative number, which will then turn my specific heat capacity back into a positive number, which is what it should be. So again, you want to be really careful with the signs, that you get everything correctly. So we're going to take our number, our 1202.9, we're going to divide it by, bless you, 52, divide it by 27.5 minus 99. And that's going to give me here on my calculator, I'll just go to the top here, 0.32353. There were probably enough digits there, and we'll round in just a second. By the way, in this last calculation, none of these units cancel, and they're all still there. This would be joules per gram per degree Celsius, which are the units we expect for specific heat capacity. We're going to get to the rounding part here in a second, but any questions on the calculation part here? Now, let's take a look at where we really should end up with our final answer. The first calculation we did was right here with our water. We're multiplying. This is 3 significant figures. That is 4 significant figures. I think when we subtract right here, we end up with 2 significant figures, which means technically speaking, this number should have ended with the 2 here at 2 significant figures. Now we come to our last calculation. This number technically should have been 2 significant figures from above. This is 3 significant figures. And when we do that subtraction there of 99 minus 27.5, I think we end up with 3 significant figures. That means that way back here, based off of the first calculation, we actually should end up with 2 significant figures in our answer. That means that we should end up with 0.32 joules per gram per degree Celsius. Any questions on that? This is probably the most common way that you can figure out how much energy is happening in a chemical reaction as well. Water is used, because we know the specific heat capacity of water, it's used a lot to figure out how much energy is being released or obtained in a process. Also, how much energy is being released or absorbed in a chemical reaction. Because in a chemical reaction, if you use reagents, most reagents are water-based. So even if you don't know the specific heat capacity of the actual chemical you're using, because it's probably dissolved in water, and water is the major component, we oftentimes can use just water specific heat capacity and figure out how much energy in a chemical reaction, like if you took an acid and base and mixed them together, and figured out how much energy is either gained or released in that process. That means literally you can figure out a energy situation in a reaction like you're going to do next week, and very commonly take a few styrofoam coffee cups and a lid and a thermometer. And that's pretty much all you need. You just need a thermometer, some nice insulated cups, and some water, and you could follow the change in temperature of water, and you could figure out, did the water gain energy, right? And you can figure out how much energy was released as a result of that reaction. You could also figure out if the water actually released energy, right? And you could also figure out how much was gained by something else. So what happens if I didn't, for example, take my metal that was really hot, but I instead put my metal in the freezer? When I put my metal in the freezer and take it out and put it into my room temperature water, which way is the heat going to transfer? So if I take this guy out of the freezer, and this is still room temperature water, in this case, the room temperature water is actually hotter than the metal at this point, right? So energy is actually going to flow into the metal, which means in this situation, the water is exothermic, right? And the metal here is going to be endothermic. So it can't go both ways, yeah? So that flow of energy can't go, into the water, or the water could actually flow energy into whatever you put in there. So it can go both directions. It's always, again, that hot to cold. But this is a very simple thing, which is known as calorimetry. It's also called coffee cup calorimetry, because simply all you need is a thermometer and basically follow the change in temperature of water. That is because when you do reactions like this, for example, and you do it under constant pressure, you do these reactions under constant pressure, when you calculate Q, that will actually equal the delta H of the reaction, that change in enthalpy. So by just using coffee cups, a thermometer for certain reactions or a lot of reactions, you could actually just determine the delta H or the change in enthalpy of that reaction by just simply a thermometer and watching the change that occurs in the temperature. So again, when we have heat transferred from one object to the next, it will result in no gain of energy. And the sum of when you add the water and the metal together should equal 0. This is essentially Q of the metal is equal to negative Q of the water, except they're all on the same side. So if you take both of these guys and add them together, it should equal 0. But if you need to solve for something, you may have to move that to the other side. And that negative distribution is really important. Otherwise, you'll be adding when you're subtracting, or subtracting when you should be adding. So when you do that, you got to take it to the other side. All right, so why don't you give it a go here, see what happens. We got a 110-gram sample of metal at 55 degrees, or 55.5 degrees Celsius, raises the temperature 150 milliliters of water from 23 degrees Celsius to 25.5. What is the specific heat capacity of the metal in joules per gram per degree Celsius? So take a few moments there, see what you come up with. Okay, so let's take a look. So it's kind of pretty much the same situation we were just talking about. So we definitely got a metal and we got some water. I'm going to put the two together. So we basically have our metal, and for our metal, we know it is a mass of 110 grams. It has an initial temperature of 55.5 degrees Celsius. We also have water, obviously. And for our water, we have a volume of 150 milliliters. We have an initial temperature of our water, which is 23.0 degrees Celsius. When the metal obviously goes for a swim there, the temperature here will rise to 25.5 degrees Celsius. We're looking for our specific heat capacity of our metal. In terms of the water, we always know the specific heat capacity of liquid water. That's that 4.184 number. So we already know this guy. By the way, that is usually never given to you in a problem a lot of times. So just assume you kind of know it. Even in book problems, they just kind of assume you know it. One of the other things we know is when we put that metal into that water, its final temperature should end up as the same as the water's final temperature, right? So although we are only told that the water's final temperature is 25.5, because the metal's sitting in there, we will know that the metal will also rest to a temperature of 25.5 as it comes to equilibrium with the water's temperature. Any questions on that so far? Once again, very commonly, like we see here, we really have enough information for water to figure out how much heat in this case, by the way, who should be absorbing the energy in this situation, the water or the metal? The water in this case. Again, the metal was 55 degrees to begin with. The water was 23 degrees to begin with. So in this case, it is the metal that's going to release the energy to the water. And we see that as a result of the water's final temperature, right? It went from 25 up to 27. So it increased in temperature in this particular case, or 23 to 25 in this case, and it increased. Now, one of the things we don't have is the mass of the water. We were only given the volume, but another number that you should always have in your head, bless you, and that we talked about is the density, right? Density is mass over volume. The density of water, as we talked about, if you need to ever use it, is 1 gram per milliliter. So since we do have the volume and we do have the density of water, we could actually use the density to figure out the mass by just multiplying here it by 1 gram per milliliter, which is the density of liquid water. Milliliters will cancel. Makes it nice now that we have 150 grams of water. So this does pop up in questions along the way in chemistry. Again, sometimes you may need the density of water not given to you either. That 1 gram per milliliter is just a number that you should know, and you could use as a conversion. Any questions on that there? All right. So now that we have everything, let's take a look at the water situation. So Q of the water in this case, ms delta T. Popping in our numbers, we have our mass of 150 grams. Again, not milliliters, but grams. Our specific heat capacity of liquid water, 4.184 joules per gram per degree Celsius. And our final temperature of the water, 25.5 minus our initial 23.0 degrees Celsius. That's going to get us here 150 times 4.184 times 25.5 minus 23.5, probably better the right number. And that's going to give us here a positive number of 1255.2 joules. This indicates, as we expect here, that for the water it is endothermic, as it is absorbing that energy in this particular case. Any questions there on that part of the calculation? Because we're doing the calculation for how much energy the water gained in this case, or how much heat the water gained. So we don't want to use the metal at this point, right? And that's basically this process of what we see in this thing, and what you'll do is, again, using water's information and temperature, because we always know the specific heat capacity of water. So we kind of always know that. So it's kind of like a constant. So just by following the change of what happens with water, it allows us to understand what's happening with the other object, or what's happening in the reaction. Now, we can now turn our attention to the metal, which is what we're kind of trying to basically find. And in this case, we're going to use our same equation, but for the metal, and that's going to be ms delta T. Once again, we are solving for S, so we're going to divide both of those guys to the other side, and that's going to give us S is equal to Q of the metal divided by m delta T. Once again, once we determine that that is the amount of energy that was absorbed by the water, as we've talked about previously, the only thing that provided energy to the water was the metal. So now we know how much energy was lost by the metal in this case. We could use our Q of the metal is equal to negative Q of the water. That means that Q of our metal will be the negative version of this, 1255.2 joules. Once again, negative because it's exothermic for the metal. It's releasing that energy to the water. Now that we have that, we just got to plug it in. So negative 1255.2. Once again, I'm not rounding until the end here since we're continuing on with the calculation. The mass here for the metal, and this is why we now want to use the metal because we're doing our calculation for the metal, 110 grams. And once again, final temperature minus initial. So final temperature 25.5 minus 55.5 degrees Celsius. Once again, that's going to provide us that negative number we need to really sort of cancel out the negative number that's up on top to turn it into a positive number. So we'll take 1255.2 divided by 110 divided by 25.5 minus 55.5. And we will end up with here, I think this number, 0.38036. Once again here, none of the units are going to cancel. Joules per gram per degree Celsius. Any questions? Yeah. I'm not sure. I punched that in. Did I? Well, let me check. I probably hit the wrong number in my head, I bet. I just want to make sure you're paying attention. All right, just like relax. All right, we're all human here, you know. Calculator screwed up. I mean, come on. All right, try that there. Minus 23. I don't know what I did there. Yeah. How about like 1569? Sound better? Yeah, you know. There you go. I think I just did the last made up a problem I did a second ago. So, you know, you want to punch that in correctly. That would probably be quite helpful, I imagine. And then that will switch there. And obviously that will switch there. And I guess that's why they invented erasers. All right, so let's try that again here. We'll just cut it out of the video. Nobody will know. All right, that'll be good. All right, so no, I'll leave it in. All right, 1569 joules. Thank you. And by the way, here, grams cancel, degrees Celsius cancels. That means up here, we got a negative 1569 joules, a negative 1569 joules, and one more eraser there to pretend like it never happened. Let's see here, we'll get rid of that there. All right, let's see what we did here. Here we go. All right. 1569 divided by 110 divided by 25.5 minus 55.5. All right. How about a 0.47545? Better? It's good. It's good. I was right with you. Yeah. All right. All right, let's talk though about sig fig. So once again, since we didn't really round, and again, I would avoid rounding to the end, especially if you're going to kind of take that number like we did there. On our first set of calculations here, we had four significant figures. When we subtracted that, I think that's 2 sig figs we should end up with, which technically means we should have been over here. And that would mean that's 2 significant figures. That's more than that. That's 4 significant figures. And when we subtract that, that's at least 3 sig figs, I think, probably. That means we should end up at 2 significant figures, so like a 0.48 joules per gram per degree Celsius in this case. Any questions on that? This is a very, very common way, like I said, to sort of figure out where that energy is transferring, how much energy. Again, just by simply using water. It's a pretty simple way in a thermometer. Any questions on that there? All right. Now, we talked a little bit about this earlier, but just a reminder that, you know, there is another sort of calorie unit that's sometimes used in terms of energy, and that's sometimes referred to as a nutritional calorie. And a nutritional calorie does have a capital C, and one nutritional calorie with a capital C is actually equal to 1,000 of the little calories, and that's 1 kilocalorie in this particular case. A calorimeter is an apparatus that's used to determine the number of calories in the food. This, for example, is sometimes referred to as a bomb calorimeter because you have a pretty insulated container. You have water, you have a thermometer, and you got like your chocolate chip cookie, whatever it may be. Got some wire with some oxygen in there. You could ignite it, and as your food starts to burn, it's going to release energy into the surrounding water. And by just simply doing a Q equals MS delta T calculation like we just did, you could actually figure out how much energy was absorbed by the water from your chocolate chip cookie and relate that to how many nutritional calories that would be. Obviously, they came off to do that. So this is a simple sort of process where you can figure out something like nutritional calories that you see like on food and stuff like that. Years ago, they used to let you do it like they would have you take a Cheeto or something like that and like a soda can with some water in it, burn the Cheeto underneath the soda can, and all the energy would transfer to the water. You could figure out how much energy was in, your chip or whatever it may be. But this is what is known as Monk calorimeter. Now, one of the things we will not worry about in this class, but you might actually see maybe in the book or maybe online, is sometimes the calorimeter itself has sort of a heat capacity associated with it. We're not going to worry about that. So if you do come across it, don't worry about it. We're just going to simply kind of just do the calculation like that. But you will see sometimes there's a certain amount of heat associated with the calorimeter itself. Sometimes include that in the calculation with it. Speaking of nutritional calories, food does have a caloric value, and there's three major types of sort of food that we come across: carbohydrates, fats, and proteins, and they all have a caloric value. Carbohydrates and protein are 4 kilocalories per gram, basically. And fat is something like 9 kilocalories per gram. Remember, a kilocalorie is basically a nutritional calorie in it. So, for example, if you were to look at any food item that you have on the nutritional label, candy bar, whatever it may be, bag of chips, healthy food as well, probably. You will see those three things usually listed on the nutritional label: how many grams of carbohydrates there are, how many grams of protein, how many grams of fat. They use really this calculation here, add them all together, and that's how you get how many calories, where it shows you at the top per serving that you have on your nutritional label. So, if you had something like, 5 grams of protein in whatever you're eating, 3 grams of carbs, and 2 grams of fat, you can do this calculation by just basically taking my 5 grams of protein, times it by the caloric value for protein, which is 4 kilocalories per gram. Grams will cancel, gives you 20 kilocalories for protein. You take your 3 grams of carbs and do your caloric value for carbs. Grams cancel, gives you 12 kilocalories of carbs. And then you could do your fat there, 2 grams of fat. Caloric value for fat, 9 kilocalories per gram. Will cancel, get you 18 kilocalories per fat. You add all that together, you're going to go with the calculator, since apparently, well, maybe I shouldn't, it didn't work out so good last time. Let's see. It didn't work out good this time because I lost a number. It's a banner day. Is it 50 on the nose? Not that bad. I like it. Yeah, it's 50. I should just added it. That would be good. That's 50 kilocalories, which is 50 nutritional calories. I would say if you look at a lot of labels and you actually do the calculation, a lot of times they round down for some weird reason why they might want to round down on the calories than up. But that's how they get, again, to those sort of calories per serving. Obviously, if you were swimming, biking, doing some type of exercise, you can figure out how much you would need to exercise to burn off those calories. Or just eat it and don't worry about it. All right. So constant pressure calorimetry, as I talked about, and as we'll actually do next week in lab, can be done, like I said, with just really some coffee cups, styrofoam cups, really insulated cups, a lid and a thermometer. And it's a super easy way to do reactions, actual chemical reactions as well. And as I mentioned earlier, if you do this in constant pressure, the delta H of the reaction will actually equal Q at constant pressure. And it's just a simple way for actual chemical reactions to sort of figure out the delta H of that reaction. Also, like I said, you could use it like we did in those problems, and we'll do next week. You can take some hot metal, throw it into some water, figure out like the specific heat capacity of a metal or a substance by again just following the changes in water. Again, because we know the specific heat capacity of water, and all we need is the temperature change. It allows us to relate what's happening to whatever went into that water. We'll skip that calculation. We kind of just did it there. The last thing we're going to talk about in this chapter is thermochemical equations. And thermochemical equations are essentially equations that have an energy component with them. So they're a balanced chemical equation, and really like the delta H value that tells you how much energy is either given off or absorbed in a reaction. So this is really the melting of ice here. This is solid ice going to liquid water. Delta H for that reaction is 6.01 kilojoules. That's actually the heat of fusion, which we'll talk about in a later chapter. Now, let's say we weren't interested in taking ice and melting it to liquid water, but we're actually interested in what happens if we had liquid water and we wanted to make ice. So if we had that situation, we would reverse this reaction. So as we go from here to here, we reverse the reaction, which means our reactants became our products and our products became our reactants. So in this case, we're going from liquid water to ice. The only difference when you do that is the sign changes. So when we go from ice to liquid water, that's an endothermic process, right? Energy has to be put in. Our energy value here is positive. When we go from liquid water to ice, liquid water has to lose energy, release energy to slow down to go into the solid phase. That's an exothermic process. And the only difference here is the sign. It will be the exact same number. So if you ever have an equation, for example, you had A plus B goes to C plus D, and the delta H for that reaction is 50 kilojoules. But you want to know how much energy would be C plus D goes to A plus B. All you simply do is change the sign. So it goes from positive to negative. And if it happened to be negative to start with, it would go from negative to positive. So if you had that same equation, but the delta H was a negative 50, when you would reverse that guy, the delta H would then become a positive 50 kilojoules. So if you have a delta H value or an energy value associated with a reaction, if you reverse the reaction, the only thing that changes is the sign. So either it goes from positive to negative or negative to positive. The number stays the same. And that is because if you remember how we calculated delta H, we took the delta H of our products minus the delta H of our reactants, which means when you reverse the reaction, your products become your reactants become your products. The difference is the same, but now you might have a smaller number minus a larger number versus a larger number minus a smaller number. The number will be the same. The sign will be different. Any questions on there? Now, sometimes maybe you don't need one of something, but maybe you need two of something. So for example, if we look at this equation here and this one here, the only difference is I took the top equation here and multiplied it by 2. That gave me 2 waters on both sides. When you do that, if you have an equation where you have to multiply everybody by a common number, what happens to the delta H value is you multiply by the common number. So this reaction where there's 2 waters starting with, or 2 ice cubes, versus 2 moles of ice cube really is what that is, versus 1 mole of ice in the first one, the delta H will be 2 times the original value. So 2 times 6 gives us 12 for the 2. By the way, if I need to divide by a common number, you divide the delta H by that. So if you had 2 waters, which was solid, goes to 2 waters, that's liquid, and the delta H is 12 kilojoules. If you wanted just 1 water on each side, you would basically need to divide by 2 all the way across. Everybody's coefficient in front by 2. That means when you get to here, you also need to divide it by 2. Gives us our delta H is 6 kilojoules. So if you ever need to reverse a reaction, and what that does to the delta H is changes the sign. If you need to multiply a reaction by a common number, maybe I need to multiply it by 2, I would multiply the delta H by 2. If I need to multiply the equation by 3, I would multiply the delta H by 3. Or if you need to divide in a reaction by a common number, you divide by whatever you're going to be dividing by the equation by. If I have to divide everybody by 2, I would divide the delta H by 2. If I divide by 3, I would divide the delta H by 3. So these are sometimes the way that we manipulate equations. The last thing that we sometimes will do is maybe we have two equations that need to be added to each other. So maybe in the first one, delta H is 50 kilojoules. Then the second reaction, I'm going to try to learn the alphabet here, E plus F. How's that? Delta H is going to be, we'll go with negative 25 kilojoules. Now, if I add two reactions together, or more than two, it could be 3, 4, however many reactions you want to add, what happens is whatever's on opposite sides of the arrows that are exactly the same thing, they will cancel out. So if I look at this, there's a C on the left side of this arrow, and there's a C on the right-hand side of this arrow. They essentially will cancel each other out. There's a D on the left-hand side of the arrow, and a D on the other equation on the right-hand side of the arrow. They will cancel out. Now, in this case, they completely cancel out because there's one on each side. It's like subtracting it to the other side. If there was like two D's on one side and one D on the other, it would just reduce down. So the one D would go away, and you'd be left with a D. You're basically like subtracting. Once you get rid of everything that cancels out or reduces down, you add these equations by keeping everybody on the left-hand side of the arrow together. So this would be A plus B. And on the right-hand side of the arrow, the only thing we have left is E plus F. This gives us what is known as the overall reaction. Now, what is the delta H of this overall reaction? It is found by simply adding those two numbers together, those two delta H numbers together. And that would get us 50 plus a negative 25 kilojoules. I'm going to try without the calculator here. Give me 25 kilojoules there. That, by the way, would tell us that this overall reaction is endothermic or exothermic. It's endothermic, positive delta H at the end. So that's a very common thing that sometimes you have equations and you kind of want to build an overall reaction from these different individual equations. It's what's known as Hess's law. We used to talk a lot about it in this class, but you won't until you get to 1A. But with Hess's law, you basically take a bunch of individual reactions, and sometimes you may have to flip them around. Sometimes you may have to multiply by a number until when you're able to add all those individual reactions together, you make like the reaction you're looking for, the equation you're looking for. And you can figure out the energy of that equation by using the individual energy values for each of those added together.